Right, in this last example video for our 3-2 lesson, we're going to compare two polynomial functions. So Carolina's profit, y equals p of x, is represented by the graph. I guess this is the same Carolina. We got our wind chime up here. That's cool. All right. Her neighbor Kayo's profit from selling X decorated flower pots can be modeled by the function shown. So here is Kayo's flower pots, and this describes the profit that Kayo will make. So the question we're being asked is, find the y-intercept of each function. Who would lose more money if neither person sold any items? So I'm going to go to the graph first because visually we can find the y-intercept of this graph. The y-intercept is when we haven't sold anything because our x is representing our number of items we're selling, whether it's wind chimes or flower pots. So if you haven't sold any wind chimes, Carolina, her y-intercept is 0, negative 64. So let's make a note of that. Carolina, her y-intercept is 0, negative 64. Kayo, his y-intercept, well, we don't have a graph, so how do we find y-intercepts again? You can find a y-intercept by plugging in a 0 for all of the x's. So if we just think about that off on the side, maybe we can do some math up here. Plug in a 0 for every x. We have 0 times negative 3 times, oops, that's supposed to be a 0, times 10. Well, 0 times anything is just 0. So Kayo's y-intercept is 0. So what this negative 64 means for Carolina is that if she has not sold any of her wind chimes, she's down $64. So she had some startup costs of $64. So she's losing money if she doesn't sell anything because she had those startup costs. So she doesn't make any money until she starts selling more of them. Now Kayo, his y-intercept is 0. So if he hasn't sold anything, he doesn't lose any money. It did not cost him any money to start his business. His startup cost is 0. So if the y-intercept, who would lose more money if neither person sold any items? Caroline is losing more money because she had a startup cost to her business that Kayo did not have. All right, part B, interpret the end behaviors of the functions. So the end behavior, we can see, let's look at Carolina's end behavior. So as x approaches positive infinity, that's just the right side of your graph. And if you look at this, we're not even going to worry about the left side of the graph because we're not making negative number of items. So we're just going to focus on the right side of the graph. Our function is going down. So as x approaches positive infinity, the y's are approaching a negative infinity. So what that's showing in this particular example is Carolina's only making money when her function is positive up here. As she starts selling more and more, her profit goes down and is approaching negative infinity. So there's a finite number of flower pots that she can sell and still be profitable. Finite means she can't just sell them forever and ever and ever and make money. Business doesn't always work that way. All right, let's talk about Kayo. What is Kayo's end behavior? Well, we don't have a graph for Kayo to look at it. We do have a function, but it's not in standard form. So can we get Kayo's function in standard form? His is r of x equals x times x minus 3 times 10 minus x. If his function is in standard form, then we can evaluate the end behaviors like we learned in our first lesson. So to get this into standard form, we're just going to multiply it out. We're multiplying an x times an x minus 3 times a 10 minus x. So just multiply the first two, and then we'll carry down the third to multiply. X times x is x. I'm going to do my work over here because it wasn't letting me move this very well. Is x squared. X times a negative 3 is negative 3x. So we just did this first multiplication. Now we're going to carry over our 10 minus x, and let's go ahead and multiply this out. Distribute the first term. X squared times 10 is 10x squared. X squared times a negative x, so that's positive times negative, so negative. X squared times x, add your exponents and you get x cubed. Now we're going to distribute the negative 3x. We have a negative 30x. Negative times negative, a positive 3x squared. All right, so combining like terms, Kaios r of x equals, we have an x cubed, so negative x cubed. Any x squared is a 10 plus 3, so 13x squared, and then minus 30x. So there is Kaios function in standard form. Now it's letting me move it. Okay, so to evaluate the end behavior, we care about the degree and the leading coefficient. So leading coefficient is -1, degree is equal to 3. So the leading coefficient, we can look at that first. As x approaches positive infinity, your leading coefficient will tell you if the graph is going up or down. Are your y's increasing or are the y's decreasing? Because that's negative, the y values are approaching a negative infinity. And then the degree tells us what's happening on the left side of the graph, because that's an odd degree. On the left side of the graph, as x approaches negative infinity, you'll have opposite end behaviors. Y will approach a positive infinity. But that negative side doesn't make sense in the context of this question because he's making a positive number of flower pots. So this is similar to Carolina's situation where, you know, as he makes more flower pots, at some point, his profit is going down. It's going to approach negative infinity. So there is a finite number of flower pots he can make as well before he starts losing money.